All right, this is lesson 4, section 8.3, geometric sequences. You can see our learning targets there. First, we need to learn how to determine if a sequence is geometric, and then we'll determine the nth term. And then we'll look at some series, adding terms of the sequence together. First, a partial sum, where we're adding a portion of the sequence, and then we'll talk about the possibility of an infinite sum of a geometric sequence. So let's start with what a geometric sequence is. Remember in lesson 8.1, we were introduced to a sequence. It's an infinite list of numbers. In 8.2, we were introduced to an arithmetic sequence in which there was a fixed constant d added to each term. A geometric sequence is a sequence in which a fixed constant r is multiplied to each term. R is referred to as a common ratio. So as long as you're multiplying the same value to each subsequent term, and that value could be greater than 1, it could be less than 1, then the sequence is considered a geometric sequence. You can see, for an example, the sequence I have written 2, 4, 8, 16, 32. We're not adding the same value every time, because here we would be adding 2, then we're adding 4, then we're adding 8. So we know it's not arithmetic. So we can check then to see if we're multiplying by the same value every time. And to go from 2 to 4, we multiply by 2, and then from 4 to 8, we multiply by 2. From 8 to 16, we multiply by 2. We're multiplying by the same value every time, so we would say the common ratio is 2. And that's what a geometric series is. So our first learning target is simply to determine if a sequence is geometric. So we have a sequence written here, 1, 3, 9, 27. And some of these are going to be easier to identify as geometric than others. I think this one's pretty obvious that we're multiplying each term by 3. So this one is geometric. And it's also helpful to state the common ratio. In this case, r is equal to 3. If it is geometric, it'll have a common ratio. Part B. It's obvious that it's not arithmetic. We're not adding the same value every time. And remember, I did say that the common ratio can be a value less than 1, and if the terms of the sequence are decreasing, then, and if you suspect that it's geometric, then the common ratio would be a value less than 1. So to go from 32 to 8, and then from 8 to 2, and then from 2 to 1/2, we could say that we're dividing by 4, but remember a common ratio is a value that's multiplied to each term. So rather than dividing by 4, we would say it is being multiplied by 1/4. But the terms are also alternating between positive and negative. So the common ratio would be negative 1/4. So 32 multiplied by negative 1/4 would bring us to negative 8 here. But then if we took negative 8 and multiplied it by negative 1/4, we would get positive 2. If we took positive 2, multiplied it by negative 1/4, we would get negative 1/2, and so on and so on. So this one is also geometric. And the common ratio is negative 1/4. Part C, maybe a little less obvious whether or not it's geometric, and if it is, what the common ratio would be. But we're at least certain that we're not adding the same value every time. So it isn't arithmetic. Doesn't guarantee that it's geometric, but at least we know it's not arithmetic. So if we suspect it's geometric, we can try to find the common ratio by dividing the second term by the first term, and then the third term by the second term. Make sure we get the same value every time. So what I mean by that is if I took the second term and divided it by the first term, we get 3/2. So at least the ratio between the first and second term is 3/2. Now, is that the same ratio from the second to the third term? So from here to here, is it 3/2? Well, if I took 9 and multiplied it by 3/2, then we would get 27/2. So looks like we have 3/2 there as well. Now to go from 27/2 to 81/4, let's see if we multiply that by 3/2. 27 times 3 is 81, and 2 times 2 is 4. So it looks like we're multiplying by 3/2 there as well. So this is geometric. And the common ratio is 3/2. Now that brings us to our second learning target then. Once we determine that a sequence is geometric, it's helpful to describe the sequence using an nth term or an explicit formula, as we did in section 8.2. Now if you recall, the arithmetic sequence in section 8.2, the nth term formula was a linear function because a common ratio, or excuse me, a common difference between terms was similar to a slope of a linear function. And so the nth term of an arithmetic sequence resembled y equals mx plus b form. Now if we wanted to use that same type of visual example, let's take that sequence we started with at the beginning of the lesson, 2, 4, 8, 16, 32. If we were to represent this graphically, first term is 2, second term is 4, third term is 8, fourth term is 16. You can see the shape of this is not linear, it's exponential. It resembles an exponential growth function. So the formulas, the nth term formulas or the explicit formulas for geometric sequences are going to use exponential functions. So you can see here, if I have just a general sequence, a sub 1, a sub 2, a sub 3, if it's geometric, then I'd be multiplying by r every time. So to go from the first term to the second term, I have to multiply by 1r. So a2 here is equal to a sub 1 times r. If I wanted to go to the third term, then you can see here I've got the first term multiplied by 2 common ratios. If I wanted to move to the fourth term, then you can see the fourth term, I've got the first term multiplied by 3 common ratios. So the number of times I multiply by the common ratio is always one less than the term in the sequence. So it's the fourth term, I have 3 common ratios. If it's the third term, I multiplied by 2 common ratios. So another way we could represent this, for example, is first term times r squared, or this one is first term times r cubed. So in general, the nth term is first term times r raised to a power that's 1 less than n. So a sub 1 multiplied by r to the n minus 1. That's the nth term. So in order to determine an nth term formula, all you need is the first term common ratio. So to practice, this is what your homework's going to look like. It'll start out easy. They'll just tell you straight up, all right, first term's 4, common ratio is 3, find the nth term. All you got to do is follow that formula. So the nth term here would be first term a sub 1, which is 4, and then your base is 3, to a power of n minus 1. More likely, though, they're going to give you a portion of the sequence, and they may ask you first to determine that it's geometric, or they may tell you that this is a geometric sequence, find the nth term. Here, the directions say find the nth term of the geometric sequence, so it's implied that every sequence that follows would be geometric. So we just need to figure out the common ratio. We know that this is the first term right there. So a sub n is -8. What we don't know then is that common ratio r right there. So what are we multiplying -8 by to get to -2, and then to -1/2, and then to -1/8? What we're multiplying by is 1/4. Rather than describing this as dividing by 4, geometric sequences have a common ratio that's multiplied to each term, not divided. So the common ratio would be 1/4 to the n minus 1. Now it can be helpful to check your formula by using the nth term formula to generate a couple of terms of the sequence to make sure you end up with the same sequence you started with. What I mean by that is, let's say we had started just with this formula and the directions were use the formula to write the first 5 terms of this sequence. Well, to write the first term, we would plug in an n equals 1. 1 minus 1 is 0. 1/4 to the 0 power is 1. And 1 times -8 is -8. So the first term would be -8. Now to find the second term, we would plug in a 2 right there for n. 2 minus 1 is 1. 1/4 to the first power is 1/4. 1/4 times -8 is -2. So the second term would be -2. Now the third term, we would plug in a 3. 3 minus 1 is 2. 1/4 squared is 1/16. And -8 times 1/16 is -1/2. So we've written the first couple terms of the sequence, comparing it to what we started with. It's the same sequence. So this is the correct formula, or explicit formula, or this is the correct nth term for that sequence. Okay, part C, go ahead and pause the video and give it a try. Try to generate the nth term formula using the first term and the common ratio. So first term obviously is 7. And knowing that it's geometric, because the directions stated that each of these sequences are going to be geometric, knowing that it's geometric, we just got to find a pattern. What's going on with our numerators and what's going on with the denominators? It looks like the numerators are just increasing by 2, by a factor of 2, I should say. So they're being multiplied by 2. Excuse me, it looks like the denominators, 7/1 And then we have a denominator of 3, denominator of 9 is 27. Looks like the denominator is being increased by a factor of 3. So I would say that the common ratio is 2/3. If we multiply this by 2/3, whoops, 2/3, there we go, we get 14/3. If we multiply 14/3 by 2/3, we get 28/9, and so on and so on. So first term is 7, common ratio is 2/3. Therefore, the nth term would be 7 times 2/3 to the n minus 1. Now, part of this second learning target still would be a problem like this, where they give us random terms rather than the terms of the sequence in order. So we don't know the first 3 terms, but it says the fourth term's 12, and then we don't know the fifth term, we don't know the sixth term, but we know the seventh term is 32/9, and so on and so on. Find the nth term. Well, the biggest help here is knowing this right there, that the sequence is geometric. What that means is I'm multiplying by r here to get this term, and then I multiply by another r here to get this term, and then I multiply by another r to get that term. So just looking at what I've drawn there, if I start with 12 and I multiply it by 3 r's, or r cubed, according to that I should end up with 32/9. So right off the bat, we have an equation that we can solve, and we're solving for r, which is the common ratio, and we need the common ratio because remember the nth term is first term multiplied by r to n minus 1. So r is an important part of the explicit formula, or the nth term, and solving this equation here can help us find that. So if we divide by 12 on both sides, then we're going to get r cubed equals 32 divided by 108, and that is equal to r cubed is equal to 8 over 27. Now at this point we can cube root and cube root to solve for r. R is equal to, the cube root of 8 is 2, the cube root of 27 is 3. So we have the common ratio is 2/3. So all we're missing then is the first term. So another way we could solve for the first term, well, let me show you 2 ways. We could just backtrack 4 or 3 terms by using our common ratio. You could do that. Depending on where that term lies, if they had given us, for example, the 19th term, then backtracking 18 terms to get back to the first could be a little tedious. So another way we could do this is just using one of the terms we know. For example, we know the fourth term is 12. So we could say, using this nth term formula, now that we know r, we could say a sub n, I'm going to substitute 12, the fourth term, so 12 is equal to an unknown first term. I know the common ratio is 2/3, and this right here was the fourth term, so n is equal to 4 minus 1. And we could solve this equation 12 equals a sub 1 times 2/3 cubed. 12 equals a sub 1. 2/3 cubed is 8/27. And then if we multiply by 8/27, or rather we would multiply by the reciprocal of that to get a sub 1 isolated. So I would multiply by 27/8 and multiply here by 27/8. And then multiplying that together, that's equal to 81/2, which is our first term. So we can now complete the nth term formula. If we had, let's see, right here, it's first term 81/2 times the common ratio 2/3 to the n minus 1. Like I said in the previous problem, or the previous examples, it's not a bad idea now to check once you've developed an nth term that you think is correct. Use that nth term to generate some terms of the sequence that you had to make sure it matches. So the problem we started with said that the fourth term, for example, is 12, so this nth term formula should give us that exact same value. So just checking that, the fourth term then would be 81/2 times 2/3 to the 4 minus 1 power, which is 3. So this is 81/2 times 2/3 cubed, which is 8/27. And then multiplying this together, 2 goes into 8 4 times. And then we can say that 27 goes into 81 3 times. 3 times 4 is 12, so verifies at least the 12th term is, or sorry, the fourth term is 12, which is what it said in the problem. And we could verify also that the 7th term will be 32/9 using that same technique. At any rate, that right there was our nth term. Okay. Brings us now to our third learning target, a partial sum of a geometric sequence, also known as a series. When we start adding values or a number of terms of a sequence together, it forms a series. So we have first term plus second term plus third term plus fourth term plus a certain term there. This forms a series, or a partial sum of a geometric sequence. If you remember or recall from our last lesson, 8.2, Mr. Gauss was able to take an arithmetic sequence and come up with a quick formula to add a certain number of terms together, rather than having to manually add 100 terms, for example, by hand. There was a formula that could be used there, and it's a similar idea for the partial sum of a geometric sequence. It wasn't Friedrich Gauss this time that developed this one. So let's use this statement that there's a partial sum that exists for this geometric series. If we reverse this and say, all right, I'm going to have this same sum, but I'm going to multiply each term by an extra common ratio. So then, now the first term becomes a sub 1, but multiplied by r. So I'm going to write that here. And the second term would be r squared, third term. And I do have one of these, but then since I've multiplied by an additional r, my last term would be a sub 1 times r to the nth power. And then if I subtracted these together, then these terms would all cancel out. But what I would have is this term minus that term. On the right side, I'd have a sub 1 minus a sub 1 times r to the n. Over here on the left, I would have the sum minus r times the sum. So if I do a little bit of factoring here, and then some dividing, I come up with the sum of the partial sum rather of a geometric sequence is first term. Let me write that a little bit neater, I apologize. First term times 1 minus r to the n divided by 1 minus r. This is partial sum of a geometric sequence. Now, this first learning target really is just a matter of using this formula then to find partial sum. Let's make sure we're clear though on what each part of this formula means. A sub 1 here, that's obviously the first term. R here and here, remember that's the common ratio. N is the number of terms we're adding. So if we're adding the first 10 terms, we would say that n equals 10. If we're adding 100 terms, then n equals 100. So it may be presented to you where rather than looking at the sequence, it's just, all right, first term, common ratio, n equals 4, you plug it into the formula, use a calculator. So to set it up, he would say the sum is first term multiplied by 1 minus r, to the fourth power, and then that's divided by 1 minus r. And by no means are these meant to be done by hand. This is most definitely something that you would plug into a calculator, and just have to be careful with what you're doing on your calculator. There is a big possibility of user error when plugging this in. I personally wouldn't plug this whole statement in at once to hit enter. I would plug in parts of it and then combine each part. For example, I would do this on my calculator first, 1/3 to the fourth power, then subtract that from 1, then I would multiply it by 2/3, and then divide it by its denominator there. So just be careful when you're plugging that into a calculator. This particular value, if correctly plugged in, would be not terribly difficult to do by hand. I'm not suggesting that you do any of these by hand, but just for the sake of argument here, 1 minus 1/3 is 2/3. So then the 2/3 there would cancel. 1/3 to the fourth power is 1 over 81. So we are left with 1 subtract 1 over 81. And then 1 could be turned into 81 over 81. So 81 over 81 subtract 1 over 81 is 80 over 81. And again, I do not suggest that you try to do these by hand. Much more efficient to do them on a calculator. So part B, much less information given to us. We do know first term, but what is the common ratio and how many excuse me, how many terms we're adding together. This is not just 4 terms that we're adding together. If you look there, there's a number of terms in the middle missing. So we need to determine how many terms we're adding together there. So the first term is 5,120. We need the common ratio, and we need the number of terms. So we're assuming that this is a geometric series. The directions didn't quite clarify that. It just said find the partial sum of each sequence. It should say find the partial sum of each geometric sequence, which would imply that this is a geometric series. So to find the common ratio, we could take any term and divide it by the term previous. For example, just the first term and the second term. If we divided the second term by the first term, that would give us the common ratio. So 2,560 divided by 5,120 would give us our common ratio, and that would be 1/2. So the common ratio is 1/2. So what we don't know then is what spot in the sequence is 20. Is it the 10th term? Is it the 40th term? We could simply now that we know what the common ratio is, we could continue this portion of the sequence until we get to 20 and see how many terms that takes us. If it's not too many, then that wouldn't necessarily be a tedious task, but let's say that 20 happened to be the 50th term. You wouldn't want to take the time to write out each term of the sequence until you got to the 20th term. So we could use an nth term formula. We know that the first term is 5,120. The common ratio is 1/2. So this is our nth term. And we could use that to find out which term of the sequence this 20 is. Now that is a term of the sequence, so I could plug it in for the a sub n and solve this equation for n. This would give me the value for n. This is an exponential equation because the variable is in the exponent. Luckily, we have talked a great deal about solving exponential equations. We use logarithms to solve exponential equations. So if you recall, this is back from chapter 5. The way that we solve an exponential equation is we isolate the exponential term. So this here is the exponential term. We would need to isolate that by dividing by 5,120. So 20 divided by 5,120 equals 1/2 to the n minus 1. And we could simplify this fraction here. 20 over 5,120 is 1 over 256. Okay, so at this point, hopefully this is coming back to you now from our last unit, or actually two units prior, chapter 5. Actually, you know what? This was chapter 4. I apologize. Chapter 4 was solving exponentials. Anyway, we need to cancel the base so that this term is no longer an exponent. So logarithms cancel bases. And because we are definitely going to want to use a calculator to get the exact value, because I want an exact value for n, I'm going to use a logarithm that is on a calculator that a calculator can use or can compute. One of those is a natural log. So I'm going to use a natural log. And you could think, well, wait a minute, a natural log doesn't cancel a base 1/2. Doesn't a log base 1/2 cancel a base 1/2? And it does, but there is no log base 1/2 on a calculator. So I am going to use natural log on both sides. That doesn't cancel the base there, like I said. But if you remember one of the properties of logarithms you can now take an exponent and move it down in front of the logarithm. So now we have natural log of 1 over 256 equals n minus 1 times the natural log of 1/2. Now I can divide by the natural log of 1/2. Now I have natural log of 1 over 256 divided by the natural log of 1/2 equals n minus 1. So last step is to add 1 to both sides. So n equals natural log of 1 over 256 divided by the natural log 1/2 plus 1. And I did say we wanted the actual exact value of n, not this value, because we need to know what place in the sequence that 20 is in. So we need to now go to the calculator, which is why we wanted a natural log, because you can do that on a calculator. So go to a calculator and plug in this expression, and it should give you the value for n. And if you plug that in very carefully, you would get a value of 9. So going all the way back, right here, n equals 9. Now, just for the sake of argument, let's say we had continued and found all those values in the middle, because 9 terms really isn't that many. So we could have said, all right, well, the third term, a sub 3, is 1,280. So then the fourth term, a sub 4, would be half of that, because remember the common ratio is 1/2. So half of 1,280 is 640. Fifth term would be half of that, which is 320. The sixth term could be half of that, which is 160. The seventh term would be half of that, which is 80. The eighth term would be half of that, which is 40. So then the ninth term would be half of that, which is 20. So it does seem to check out. And you're saying, well, boy, that was an easier way or a quicker way. And it was, because we only had 9 terms. But again, if it had skipped more than that, then it could turn out to be kind of a tedious task to manually jump to that term here at the end. At any rate, we know that that 20 was the 9th term. So we are adding 9 terms of the sequence together. So now we can use the partial sum formula, because the task wasn't to figure out what term this 20 was in. We only had to do that so that we could use the formula. The partial sum formula is first term times 1 minus r to the n, and what we didn't know was that n value divided by 1 minus r. So now we can plug some values in. First term was 5,120 times 1 minus r to the 9th divided by 1 minus 1/2. And again, this is time for a calculator. And if you plug it in carefully, you get 10,220. Could also be presented to us in sigma notation. which is actually useful, because this is the nth term formula right there. As long as we have that, then we actually have all the information we need. This is the first term. Right there is the common ratio, and we're adding 5 terms together. Now you do have to look a little more closely sometimes when given sigma notation. If, for example, they had started with a value of k equals 0, then this wouldn't necessarily be the first term. Or let's say that there wasn't the k minus 1, it was just a value of k, then this wouldn't necessarily be the first term. So just have to look carefully. And if this did, for example, start with a value of k equals 0, then you would plug in a 0 right here for k, run it through the formula to find your first term. And that is what you would use as a sub 1. And that also, let's say that we started with 0 here and went all the way to k equals 5, then we would actually be adding 6 terms together and not 5. So just look carefully at the sigma notation that you're given. But if it's given like this, then we know that the first term is 8, common ratio is 5, and we are adding 5 terms. So then we would use the partial sum formula and run it into your calculator, and we would get 6,248. Okay, this brings us to our last learning target for this lesson, infinite sum of a geometric sequence. So we've got to kind of wrap our heads around this idea for a moment, because what this is saying is that we are going to take all the terms of a sequence all the way out to infinity and add it all up. And at first thought, you could say, well, that's impossible because there's always going to be one more term that you're adding, and then one more term that you're adding. If you go all the way to the end of the sequence, it actually doesn't end because there's another term that you're adding and another term. So isn't the sum going to continue to just grow indefinitely if you keep adding more and more terms? And that's an interesting conversation to have. So let's take a look at this series. So 1/2 plus 1/4 plus 1/8 plus 1/16 added indefinitely. That's what these dots here imply. The common ratio is 1/2. To find an infinite sum means that n is approaching infinity. So we're not adding a certain number of terms together, like 100 terms or even a million or even 10 billion. We're adding an infinite number of terms together. So if we look at, go back one more time and looking at our partial sum formula. One notion that's really useful to have a firm grasp of, especially for those that need to move on to calculus, is this notion right here. So what I've stated here is if the common ratio, and I've put it in absolute value because the common ratio could be positive or negative. So if the absolute value of the common ratio is less than 1, so these are values between 0 and 1. If the common ratio is a value less than 1, then that common ratio raised to a power approaches 0 if that power n increases to infinity. Here's an illustration of of what I'm talking about. So I have a common ratio of 1/2, and I'm going to raise that to an increasing power. So 1/2 to the first power, 1/2 squared, 1/2 cubed. And you can see what happens to the value. 1/2 to the first power is just 1/2. 1/2 squared is 0.25. 1/2 cubed is 0.125. 1/2 to the sixth power is 0.015625. 1/2 to the 10th power is 0.00097. So you can see as I increase the exponent, then the value decreases substantially. I'm only at 20. Can imagine if this had gone 1/2 to the 100th, 1/2 to the 1/1,000,000th. What this statement means, r to the n approaches 0 as n approaches infinity. What I'm trying to illustrate is right here. This value, or these values rather, are getting smaller and smaller, but they're approaching 0 as the exponent is increasing here. So as n approaches infinity, r to the n approaches 0, but that only works if r here is less than 1. So going back to this partial sum, if r, or the absolute value r, is less than 1, then this value, r to the n, approaches 0 as n approaches infinity. So then we have 1 minus 0, which is 1, and 1 times a sub 1 is just a sub 1. So as n approaches infinity, and we take an infinite sum, this part of the formula essentially disappears because it's 1 minus 0. So the infinite sum, if the common ratio, the absolute value of the common ratio is less than 1, the infinite sum of a geometric series is that formula right there, first term divided by 1 minus r. And this is extremely important. It only works if the common ratio, if the absolute value of the common ratio is less than 1. If the common ratio is greater than 1 or less than -1, then the geometric series has no infinite sum, or you could say that it diverges. That's another word that some textbook uses. The series, or the infinite sum, diverges, meaning it doesn't come to a particular value. The opposite of that would be converges. If it has an infinite sum, we say it converges. So you have to check first if it's a geometric series. If it is, if it has an infinite sum, only if the common ratio is less than 1. Now, going back to this illustration right here, we discussed the fact that a value less than 1 that is being raised to an increasing power here, its values then start to decrease and head towards 0 or approach 0. I want to talk about what happens when you add values together where each subsequent term is getting smaller or the values are approaching 0. So using the same value of 1/2 to the power of n, the sums over here, the sum of the first term, which is just 1/2, is obviously 1/2. But if you add these first two terms right here, 1/2 plus 0.25, that's the sum of the first two terms, you get 0.75. If you have the sum of the first three terms, 0.5 plus 0.25 plus 0.125, you get 0.875. If you continue on and add the sum or compute the sum of the first 6 terms, so that would be all the way up through here, that's 0.984375. If you sum the first 10 terms, it's 0.999023. If you sum the first 20 terms, it's 0.9999990. 0.046. If you took the first 30 terms, it's 0.999 with about 12 nines on it. If you took the sum of the first 100 terms, it's 0.999 with about 1,000 nines. The point is that if you keep adding more and more and more terms, the sum, or the running total, is just 0.9999999 repeating. If you keep adding more terms, you just add more nines to the end, and the 0.999 goes on forever. So what is 0.99999 approaching? 0.999 indefinitely is approaching the value 1. And so when we say that these infinite geometric sequences can be summed, or we can find the sum of an infinite geometric series, what we're saying is that the sum approaches a value, not that it specifically is equal to a value, but it approaches a value and gets infinitesimally closer and closer to a particular value, in this case 1. Another way of thinking about this, we could say, all right, the sum of what we just talked about here was equal to 0.999 repeating. Now this is an exercise that you probably did in elementary school, turning a repeating decimal into a fraction. What we could do here is multiply this sum by 10, and then if I subtracted one from the other, I could get 9s equals 9, because the 0.999 part would be subtracted away. And if I divided by 9, then I could say the sum is equal to 1. So essentially what we proved here is 0.999 repeating is equal to 1. So what we would say is this infinite sum of 1/2 plus 1/4 plus 1/8 plus 1/16, that sum approaches 0.99999, but 0.99999 is equal to 1, so we would say the sum approaches 1, or the infinite sum is equal to 1. This is what we mean by taking an infinite number of terms and calculating a sum. It's what value is that sum approaching but not exceeding. In this case, this sum right here approaches but does not exceed 0.9999 repeating, which is equal to 1. So we're going to look at a few examples that illustrate this idea of approaching a certain value but not exceeding using an infinite sum. So to practice, find the sum, and the ... implies that this would continue adding a next term and a next term, because there is no final value that we're adding. So what's implied here is this is an infinite sum, and I apologize, the directions aren't super clear, and in your homework it'll say find the sum of the infinite geometric sequence. So you can infer here that these are all geometric, but just for the sake of practice, let's try to determine if this is geometric. So we're multiplying by 1/3 here to get to 6. We would multiply by 1/3 there to get to 2, and we would multiply by 1/3 to get to 2/3. So we are multiplying by the same value, the common ratio. So the common ratio is 1/3. That is less than 1. So this geometric series here has an infinite sum. So we would use the formula sum is first term over 1 minus r. First term was 18 divided by 1 minus the common ratio. And these aren't terribly tricky to do by hand. You are certainly welcome to use a calculator, but 1 minus 1/3 is 2/3. 18 divided by 2/3 is 18 multiplied by 3/2. So 18 multiplied by 3/2, 2 goes into 18. 9 times 3 is 27. So then going back to this notion that the partial sum here approaches 27, and gets infinitesimally close to 27, but does not actually exceed 27. So looking here, we've got that sequence, or that series, 18 plus 6 plus 2 plus 2/3. Just the sum of the first term alone is obviously 18, but if you take the first two terms and add them together, 18 plus 6 is 24. If you take the sum of the first three terms, 18 plus 6 plus 2 equals 26. First four terms, 18 plus 6 plus 2 plus 2/3 is 26.66 repeating. If you go all the way down to the sum of the first 8 terms, it's 26.996. If you take the sum of the first 16 terms, it's 26.999999373. And so if this pattern continued indefinitely, then the sum here, the sum approaches 26.999 repeating, which, as shown in this example, yeah, right there, the 0.999 really is just 1. So the sum is approaching 27. That's how we would clarify that. So looking at another example here, part B, this actually is written incorrectly. I apologize. It's not a sequence, it should be a series. So 5 plus 10 plus 20 plus 40. Idea being, does this geometric series here have an infinite sum? And 5, 10, 20, 40, the common ratio is 2. And the absolute value of 2 is not less than 1. Remember, in order to find the infinite sum of a geometric series, the common ratio has got to be less than 1. So this one has no infinite sum, or you could say the series diverges. If it has an infinite sum, you would say it converges, and then you find the value to which it converges using that formula. It could also be given or represented using sigma notation here, and we're summing from 1 to infinity, so this is an infinite sum, and this is the nth term of a geometric sequence, so this is the infinite sum of a geometric sequence. Question is it going to converge or is it going to diverge? And it depends on the common ratio. In this case here, the common ratio is 1/4, and the absolute value of 1/4 is less than 1, which fits the criteria in order to use this formula to find an infinite sum. So this series here would converge, and we've got to find out what that value converges, what the series converges to using this formula. And we need to know the first term, and we need to know the common ratio. Now we already decided the common ratio was 1/4, and if we were to plug in an n value of 1 into the nth term here, then 1 for n, 1 subtract 1 is 0, 1/4 to the 0 power is 1, 3 times 1 is 3. Therefore, the first term is 3. So the infinite sum of this geometric series is first term 3 divided by 1 minus the common ratio of 1/4. This is 3 divided by 3/4, which is 3 multiplied by 4/3, which equals 4. So that brings us now to the end of lesson 8.3. So just to wrap up in your minds, we've talked about geometric sequences that have a common ratio. We've learned how to determine the nth term of a geometric sequence. The nth term meaning this formula here. We've learned how to do a partial sum using a formula. And then lastly here, we've learned how to do an infinite sum using this formula here. And that formula is only valid, or a geometric series has an infinite sum only if the common ratio, or the absolute value of the common ratio, is less than 1.